So welcome back from the weekend. Today we're going to continue on primarily with transformations on random variable as it pertains to expectation and variance. Okay, so hopefully Project 2 will be posted on the course Blackboard tonight. There's some loose ends I still have to tie together. The reading is updated. Sections 3.3 to 3.4. It's about 20 pages in the Barron book. Please get that done by a week from today. Okay. So when we last left off, we talked about this idea of expectation. And expectation is a probabilistic average. Notationally, you'd write E of x for expectation of random variable x. And so how the semantic goes, we have our value x here, x of I, and we are weighting each one of those values that a random variable can take on. We're weighting by the probability p of xi. And so this weighted average, if you will, gives you the so-called expectation, which is noted as Greek symbol mu. Sometimes, if you have multiple variables for which you're computing the expectation, you see a notation like mu sub x. And that subscript x is used to note that this particular expectation is the expectation for random variable x. And so that's often used in notation if you have more than one random variable. Now, of course, if you have a bunch of data and you don't know what the probability is for each data point, you can assume that each data point has equal probability. So if you have n many data points, you can assume the probability of each one of them is 1 over n. And so in that case, you compute as expectation this xi, which is all of the values, times p of xi, which is 1 over n if you don't know the probability, and that gives you what you know as the average, or the sample mean. Okay? And so the average is really just a simple form of expectation where you're making the assumption, because you don't have the probability for your variables, you're making the assumption, simplifying assumption, that each value is equally probable. Okay, any questions about that? Also, we have the variance. The variance is noted with Greek symbol sigma squared, lowercase sigma, and functionally we call it variance of x. And variance is nothing more than the probabilistic average for which each random variable differs from its expectation. So here we have variance of x, and then we have E of x is the variable, minus its expectation. So you could also write that as E of x minus mu sub x, right? That's the same quantity squared. That's the same as saying x minus E of x. And so what this variance measures is the dispersion or spread. And that spread is measured with reference to the notional center, and expectation is considered to be the central value for a distribution for a random variable. And so here we would write that as the weighted sum. And so here we have our sum with our sigma notation varying x. So we have the value of x minus its mean, quantity squared, and we square that because we're concerned about the magnitude and not the direction. And so we take that x minus mu quantity squared and we multiply that times the probability, p of x. And so one thing you'll notice when you write an expectation, you have E of some expression like y, right? Whenever you write the result of that expectation, you expand it out, well, you have that same value occur under the summation, and then you're going to multiply that times the probability of that value. So in addition to a straight expectation, you can have an expectation of some expression. So if I said expectation of y squared, right, that's the same as the sum, and I write my y squared times p of y. So whenever you see an expectation, you're going to repeat under the summation that expression inside of the parentheses, and you're going to multiply that expression by the probability of the variable itself. Okay. Any questions about this? Okay. And so variance measures the spread or variability, if you will, for a random variable. Okay. We also have standard deviation, which is sigma, and you'll note the relationship between sigma and sigma squared. Sigma doesn't have that square term, and sigma, the standard deviation, is purposed with fixing up the units, as it were. And so if you look at variance, let's say you have a value that measures dollars, and you compute the variance, because of that square term, you have dollars squared, which kind of doesn't make sense. And you can't really compare dollars squared to the central value, right? The expectation would be in dollars, but the spread about the central value, this expectation, is in dollars squared. And so in order to be able to make a comparison between the dispersion and the center, or expectation, the standard deviation fixes that up by taking the square root of the variance. And in doing so, now you're going from dollars squared, for example, to dollars. And so the standard deviation, sigma, is nothing more than the square root of the variance, where the variance we just went over. Any questions about this? Does that make sense? Yes. Okay. So we also talked about covariance, and covariance talks about the relationship, or the coupling, if you will, between two variables. And the example we gave in these two graphs, the economic growth versus stock market return, the graph on the left, your left, we have a positive covariance. And so one variable, let's say our x variable, might be economic growth, measured in percentage increase. The other variable, y, might be our stock market return. And so we might want to know for every unit step increase or change in x, we want to know what the commensurate unit step change is for y. And in this particular case, if you take any point on this left-hand graph and you go from one point, say that point, to the next point, this point, you have an increase in x, and there's a commensurate increase in y associated with that. That coupling, that commensurate increase in the other variable, represents a coupling, and that's measured by covariance. And so for covariance, we have the expression covariance between variables x and y. This is pairwise covariance. You can represent more than pairwise through something called a covariance matrix, which I won't talk about now, but it's just the expectation of the product of two terms. The expectation of the deviation between a variable and its center for x, and the deviation between variable y and its center. So here, this first term, x minus e of x, that's the deviation for random variable x with respect to its center. And then the second term, y minus e of y, is the deviation of variable y with respect to its center. And so if we write that out, we have these two terms multiplied, we repeat them. So here's x, our value of the random variable x, and here's mu sub x, which is the same as expectation of x. So we take that term, we multiply it by y minus mu of y, and we take that product and we multiply it by the probability, and we're literally there following the pattern, if you will, the recipe for what an expectation is. And so you'll notice here, for this expectation, everything inside of this expectation in this region here repeats underneath the double summation, and we have a double summation because we have two variables that we want to vary. Okay, so we take this product of the dispersion of x and the dispersion of y, and we multiply by the probability of x and y, right? And we sum over all values. So this is covariance, and one of the problems with covariance pertains to the units, right? So we talked about this idea for economic growth, which is percentage increase, times stock market return, which is measured as dollars. So if we compute this covariance, we would have something like percentage increase dollars. Or for world oil production, which is barrels and gasoline prices, the graph on the right rather, we talk about barrel dollars, which kind of doesn't make sense. And so to fix up those units, to make it something that's more intelligible or something you can interpret, this is fixed up, our covariance, by normalizing it, if you will. So we take the covariance, which is that unit step increase or decrease, and covariance can be positive or negative. It's negative if a unit step increase in one results in a unit step decrease in the other. We see an example of negative covariance with the graph on the right. If we go to the right, from one point to the next for world oil production, we see for unit step increase in oil production, we see a unit step decrease in gasoline prices. And so covariance can be positive or negative, and we normalize it by dividing that coupling by the dispersion, which is standard deviation in those normal units, and that gives us something that looks like a percentage scale. And covariance, therefore, varies between +1 for what's called positive correlation, perfect positive correlation. That means a unit step increase in one results in this same unit step increase in the other. We divide by standard deviation of each of these variables in order to do that normalization. And so when we do that, we get correlation, which is noted by Greek letter rho. Okay. Any questions about this? Make sense? So that's from last time. Okay, so let's begin. We're going to talk about properties of random variables. And we're going to kind of take a little bit of a sidebar and go back to basics and talk about certain rules of mathematics. And we're going to extend that to summation form of these. Now, certainly we care about transformations on random variables because sometimes you're going to multiply a random variable by a value. You're going to multiply two random variables together. You're going to change it in some fashion. And so it's a typical question with this type of stuff in stochastic computing, probability, and stats in general, to ask, if I modify my measurement in some fashion, how does the distribution change? Now, certainly you could do that modification, and then you could now plot this distribution and look at it. But rather than do that, people have developed these mathematical expressions to describe what happens pertaining to these properties. And we'll get to that in a few moments. But for the meantime, let's talk about certain rules of mathematics that we'll need for these different transformations on random variables as it pertains to variance, expectation, and covariance. And so we have the associative rule, and to jar your memory, in algebra, you talk about associative rule, which says how you group together certain operations. And so you have multiplication, so let's say you have a number of variables, let's say you have x1, and you multiply that with x2, and you multiply that with x3. Now, what the associative rule talks about is the order in which you apply these operations. And so the associative rule for multiplication says, if I take x1 and x2 and I multiply them together, and I get some result, and then I multiply the x3, that gives me the same result as x1 multiplied by the result of doing the x2 times the x3 first, right? And so that associative rule for multiplication, let's contrast that with associative rule for addition. Associative rule for addition says if I add x1 with x2 with x3, and let's say I perform the summation of x1 and x2 first, and I take that result, or sum, and then I add x3 to that result. That's the same result as if I group together first the summation between x2 and x3, and then take that result and add to it the x1. Now you might be wondering, well, gosh, why in the world are you talking about this? Okay, so when we have things like summations, it's often too tedious to describe the summation by writing out every single term. And so often more compact way of expressing that summation is using summation notation. And that summation notation is capital sigma. And for that capital sigma, you have an index, and that index is replaced with a set of values. So the index is called I in this case, and I goes from 1, so the bottom bound for that index is down below, and then the top bound is above that sigma notation. So if I said I'm going to sum together for I goes from 1 to 3 of this xi, that's the same expression if I write it out the long way of x1 plus x2 plus x3. Okay, so the expression using sigma notation on the left of equality is just a more compact way of expressing the summation. So you could imagine if instead of 3 terms, if I had 10 terms, the only thing I would change is what that upper bound is. I'd change that from a 3 to a 10 rather than writing out 10 terms separated by plus signs. Okay. Any questions about this? Okay, so what I'm going to do now is take advantage of this associative rule as it pertains to the summation symbol. And let's suppose we had an expression and we had 3 terms for a variable I'll call x and another variable that I'll call y. And let's assume that I had x1 plus x2 plus x3, and I sum together that with y1 plus y2 and something I'll call y3. Now, of course, The associative rule says that I can group together these summations in any way that I want. Now, if I'm going to group them together, one way I could say I'm going to take the first x, add that with the first y, then I'm going to take the second x, add that with the second y, and then I'm going to take the third x and add that with the third y. So the associative rule says I can group them together and it doesn't matter, I get the same result. So I could equally as well write this expression as x1 plus y1 plus x2 plus y2 plus x3 plus y3. Right? I can group them together whatever way I want. So let me do that. I'll put a parenthesized expression for the x1 plus y1, another parenthesized expression x2, y2, and likewise for x3 and y3. So that just says I'm going to perform the sums first that are in the parenthesized expression, and those results, I'm going to sum those together. Now, of course, here, if you look at this, you can write this more compactly. You can write it as a pattern, right? You see a pattern here. We have the first one, the second one, the third one. So why not write that more compactly using summation notation? So let's do that. So I can write summation. I goes from 1 to 3, because I have 3 terms, and I can just write xi plus yi. Okay, so that's one way of writing it compactly. Now, because of this associative rule, I don't have to group them that way. I can group them some other way, and it's the same expression. Now, of course, if I take this first expression, you'll notice here, I have all the x's summed together, and then I have all the y's summed together. I could equally have said, well, let me associate them or group them together differently. That would be the same as saying I goes from 1 to 3, I sum all the x's, I take that result and I sum it together with all of the y's. I goes from 1 to 3, sum all the y's together. That's the same expression. And what allows me to do that, they're equal to one another, what allows me to do that is this simple associative rule, which says that I can group together these operations in a certain way, and it gives me the same result. Any questions about this? Does that make sense? So we're going to use this in our transformations on random variables as it pertains to expectation, variance, and covariance. Okay, so let's take a look at distributive rule, right? Let's say I have an expression, and for the sake of assumption, let's say I have x1 plus x2 plus x3. And let's say I'm going to take this expression and I'm going to multiply it by some scalar variable value a. And it doesn't matter what a is. It could be 1, it could be 2.7, it doesn't really matter what it is. And so what this distributive rule says is that if I have a multiplication of this term on the outside of the parenthesized expression, and I have some operation on the inside, I can literally spread this operation times a to each of these terms, and I get the same result. So I take my times a, and I'm going to multiply that by the first term, and I'm going to apply that to the second term, I'm going to apply that to the third term. And I'm literally distributing this multiplication by a to each of those terms in the parenthesized expression. So what that gives me a times x1 plus a times x2 plus a times x3, right? And you notice here I have that common factor here. Now, going in the opposite direction, I can take advantage of distributive rule, right? The distribution of multiplication over addition, and I can factor out, and that's what allows me to factor out. So if I have that expression, I have that common a, I can factor out that a and get back my original expression, x1 plus x2 plus x3. Now, of course, it doesn't have to be a scalar. It can be a function. So let's say I had some function f of y, right? I can say x1 plus x2 plus x3, for example, and let's say I had some function f of y, right? So y is f of y is some function, and it doesn't matter what that function is. It could be a complex expression, it could be a simple expression. Here, I'm distributing the multiplication of this f of y over the sum of these three terms in the parenthesized expression. So I literally take my f of y, and I apply that multiplication to the first term, the second term, and the third term, and that gives me x1 times f of y plus x2 times f of y plus x3 times f of y. So this distribution of multiplication over addition works whether it's a scalar, a value like a, or it's a function. Okay. Any questions about this? Does that make sense? Yes. All right. So let's take a look lastly at multiplying two factors together, right? So suppose we have an expression x plus y quantity squared, right? Well, if you're squaring it, that's just the multiplication of x plus y times x plus y. And you probably learned, I don't know if it was algebra or when, you probably learned the FOIL rule, first, outside, inside, last. That's how you multiply these together, right? So first, all right, you take these first terms, right, the left-hand term, x's, you multiply them together, that would be x squared. Outside would be the y times the y squared. I'm sorry, outside is the x and y, so x, y. Inside is yx. Last is y squared, right? And you add them up, and you get x squared plus 2xy plus y squared. Now, of course, when you do this multiplication of factors, sometimes in the literature, you'll hear this respected or represented or described as the first term, the second term, and this is sometimes called the cross term, right? And so what you do when you multiply, you square the first term, so square that, you square the second term, and then you say 2 times the cross term, which is the first term times the second term, right? It's exactly the FOIL rule. Now, of course, you're used to seeing the FOIL rule applied to simple terms like this, but you can use the FOIL rule for entire expressions. So let's say we had the following expression. We said x1 plus x2 plus y1 plus y2. And let's say the x1 and x2 were grouped together, and the y1 and y2 were grouped together, and we're going to square this whole thing. Now, in that case, we still apply the FOIL rule, but the first term now is going to be the first parenthesized expression, and the second term is going to be second parenthesized expression. So in that case, if we applied the FOIL rule to this expression, so it's first squared, so we'd say x1 plus x2 squared, the second term squared, y1 plus y2 squared, plus 2 times the cross term, 2 times the first term plus the second term. So 2 times x1 plus x2 times y1 plus y2, okay? And you could certainly further reduce these by multiplying out again. And so this FOIL rule, we can actually apply not just to individual variables, but we can apply it to the sum of two terms, and each of those terms can be more complex expressions. Okay? All right. Any questions about this? No questions? Make sense? All right. So let's continue on. All right. So let's take a look at expectation. Now, of course, if you have a random variable x, you might want to take the expectation of this random variable, but you also might want to transform the x by some operation. And this particular operation is called an affine transformation. You multiply by a scalar, and then you add some value to it. So it's like a scale change, you're making it bigger, and then you're shifting the value. That might be, for example, you're converting from degrees Fahrenheit to degrees Celsius. It's a certain type of transformation that you're making. And so one of the questions you ask is, if I have an expectation and I perform some transformation on that expectation of a random variable or set of random variables, how does the resulting expectation change, right? So again, up here, I've written what expectation is, mu. E of x is just the weighted sum, xi times the probability of xi. So this property is called the linearity of expectation. We're actually going to demonstrate it and prove it. It says if you have random variables x and y, and you multiply by a scalar, it doesn't matter what those scalars are. So here I have ax, I'm multiplying x by some number, a could be positive, negative, real value, it doesn't matter what it is. And I multiply y times b, and I add some constant c. C could be any value. How does the expectation change if I have such a transformation? And so here it says, all right, well, the x part, its expectation. If I sum two variables together, the expectation of the sum is the sum of the individual expectations. So you'll notice here I have the term involving x summed to the term involving y summed with the c, right? The second thing that happens, if I multiply by a scalar, right, expectation of a times x is a times the expectation of x. So if you had some mu sub x, it would just be a times your mu, resulting from the expectation of x. So let's take a look at that operation. So we're going to take this expectation and our definition for expectation, and we're going to plug in. So instead of an x, we're going to have this expression ax plus by plus c. Okay? All right. Questions? Make sense? All right. So let's do that. So we plug in for our definition of expectation, and because we have two variables, we're going to have our double summation, and we're going to have a joint probability p of xy. So here in the parenthesized expression, I have ax plus by plus c. So I write down my ax plus by plus c. I multiply by the probability. It's a weighted sum. So I get this expression on the right-hand side of equality. I have a double sum because I'm varying over all the possible values that x and y can take on. So the first summation, I have my y here, and the other summation, the outside summation, I have my x. You could write it in the other order if you chose to. It doesn't make a difference. So here we see something. We see a p of x, it's a function, p of xy, and we're multiplying that by a parenthesized expression that involves a sum of three terms. The first term is ax, the second term is by, the third term is c. So we're going to take advantage of the distributive rule. We have some function times the sum of a bunch of things in a parenthesized expression. So we're going to distribute this p of xy with the first term, the second term, and the third term. So let's do that. So I do that, and you notice here I have three terms. I have my ax from before, I multiply by the pxy. I have my by from before, I multiply by my pxy. And I have my c here from before, I multiply by my pxy. So I've literally done the distributive rule, distributed multiplication over addition. Okay, any questions so far? No? Okay. So now, you'll notice here that I have a summation with my sigma notation on the outside, and then I have the summation of three terms in the parenthesized expression. Now, of course, I could take advantage of the associative rule for summation. I don't have to group together these three terms, the ax pxy, by pxy, c pxy. I don't have to group those together and do that sum first. I could absolutely do the other sums noted by or summarized by our sigmas, right? So if I do that, I basically can group together those individual terms, those individual sums, before I do the sum between the ax, by, and the c. Okay. So let me do that. So now I'm taking advantage of the associative rule of summation from before. That's like when I had the x's plus y's and I separated them out so the x's are under one sigma, summing together all the x terms first and then summing together all the y terms first. Here, instead of summing together these three terms first, I'm going to sum together just the ax terms, then just the by terms, and just the c terms. Okay? And so I do that taking advantage of the associative rule of addition. Okay. Any questions about this? No questions? Make sense? Yes? No? Not quite. All right. Okay. So now that I have that, I'm going to make some observations. So if I take a look at this first term here, I have the double summation, x and y, ax times p of xy. And I'll notice each term has this a out there. That's a scalar, right? And the scalar, when I look at that, that's similar to that thing that I did before where I had ax1 plus ax2 plus ax3. The summation represents the sum of a bunch of terms, but each term has an a in there. So I'm going to take advantage of the distributive rule, distributing of multiplication over addition, and I'm going to factor out that common a term. So if I do that, I'm going to get an a out front, I have my double summation, and then I have my x times p of x, y, and I sum with respect to y and with respect to x. Okay? So I'm going to do that for all three terms. I'm going to pull out the common factor b on the second term, and I'm going to pull out this common factor c on the third term. Okay? So let's do that. Now, of course, when I pulled them out, I did something on purpose here. I could pull them out of both summations, but when you have a summation, you can only pull out a variable that does not vary under that sigma notation. And what do I mean by that? So here, in this first term, I have a y here. Now that means on each iteration of this summation, and you implement a summation with a loop, this is going to go through different y values, and those y values are going to be plugged in everywhere you see random variable y. So if you have a variable that does not involve a y, for all intents and purposes, it looks like a scalar underneath that summation. But you'll notice here I have an x. That x does not get that y value. Only the random variables capital Y do. And so I can pull this x out from under the summation, factor out, if you will, as if it were a scalar. Well, a doesn't involve any y or x, but x, it involves this big X. It's going to take on values of this little x. So I can't take this big X outside of the second summation. I can only take it outside of the first summation. But the a I can take out of all summations because a is not controlled. It's called a free variable. Okay? So I do that factoring, taking advantage of the distributive rule, and I pull out my ax, the first term. I pull out the by from the second term. Now, of course, with the summation, you'll notice up here it said x was the outer summation and y was the inner summation. I can change those. And the reason why I can change the order of those summation symbols is because of associativity, right, of addition. So if you flip the additions, it's the same result. If you associate the additions differently, it's the same result. So that allows me to switch the order of those summation symbols. So I have my ax here, I have my by here, and my c, that doesn't involve x or y, so I can pull that entirely out of both summations. It's factoring out of all of those terms that I get when I vary x and I vary y. So I have this line, I have the summation along x of ax times summation of y, p of xy. I have summation along y, by, summation with respect to x, p of xy, and then lastly I have c, our constant, times summation with respect to x, with respect to y, p of xy. Okay. Any questions about this? No? Make sense? So I'm just applying these basic rules from algebra, associativity, distributive law, and then summarizing with the summation. Okay. So now I make an observation. Well, the first observation I'm going to make, if we look at this third term, I have a constant c, and I have a double summation, and I have a p of xy. Now, p of xy, that's a joint probability involving two variables, and I'm summing with respect to all possible values of x and all possible values of y. So that's like saying, let me take a probability, and I'm going to sum the probabilities associated with all possibilities of all the variables. Now remember, the law of total probability says if I sum all possible values, the probabilities sum to 1. So I'm going to take advantage of that, and this entire term here is going to go to 1, and I'm going to get c times 1, which is just c. Okay. So now I make another observation as it pertains to marginalization. Now remember that coin flip and die roll example where I had a table? And I said you have two variables and you wanted to get the probability of just one of them, and you sum along the margins. And so we'll take advantage of that. We see here we're summing for all values of y, probability of x, y. So that's going to give me p of x, and it's that same marginalization procedure that's depicted here. Likewise, here I sum all the values of x P of xy, that's going to give me P of y. And it's exactly that example for joint distribution that I gave when I talked about marginalization. So we take advantage of marginalization, and this P of xy here, because I'm summing out all the y terms, I get P of x, and then I can replace this expression, P of xy, with P of y, and this third term is now C. Okay. Any questions about this? All right. So I do that, and I'm left with the sum with respect to x of a, x, P of x, plus the sum with respect to y of b, y, P of y, plus C. Now, I can take this expression, and I notice this is a summation, so it's like a bunch of terms being summed together, and I notice there's a common a, right? That's a constant. And again, I take advantage of the distributive rule, distribution of multiplication over addition, and I can factor this out because of that. Now, if I factor this out, I have a leading a times the summation with respect to x of x, P of x, right? So I'm going to factor that out. Likewise, for the second term, I have a leading constant b. So I can factor out that b out of each term in the summation, and that gives me a b times y P of y, where the y P of y is under the summation. And then the c is just floating out there. Okay. Any questions about this? No? All right. So I do that, and I get the following result. Now, going back to our definition up above, for what expectation is just the value times its probability. So this is just the same. So I have a value of random variable x, right, that gets plugged in, times its probability. Okay, that's just the same as expectation of x. And I have my leading a out front, so it's a times e of x. Same thing for the second term. That's just b times this term. That's the expectation of y, e of y. Right? And I have that leading coefficient b plus c. So what I'm left with is a times expectation of x plus b times the expectation of y plus c. And that's my result. Okay. Any questions about this? Make sense? So it's literally just an application of these basic rules of algebra with law of total probability and marginalization mixed in. But most of the work is distributive rule for factoring and associative rule for rewriting under the summation. Okay. So it says that if I have two random variables, x and y, and I multiply them times a scalar, so that's a scale change, and then I shift them, add some constant, how the resulting expectation of this transformation works out is just a times e of x plus b times e of y plus c. And so let's say you were doing a transformation from Fahrenheit to Celsius, right? That's just a scalar, an affine transformation. So now you know what the expectation of a Fahrenheit variable looks like if you were transforming it from Fahrenheit to Celsius, okay? Or Celsius back to Fahrenheit. All right. Any questions about this? So I recommend that you try it yourself, get a pencil and paper, and you just try it yourself, get comfortable doing these transformations, and more importantly, recognizing when you're going to use associative rule, when you're going to use distributive rule, both for distribution as well as for factoring. Okay? All right. No questions? All right. So, and there's my result. So now, another result with expectation. Sometimes you want to multiply two variables together. And you might want to know, well, if I multiply two random variables or measurements together, how does the expectation change for the product of those two things? And so the result is that if I have variables x and y, so x could be global oil production, and y could be gas prices, x could be economic production, and y could be share price, right? And so let's say you want to multiply the two together. How does the expectation change if you have a product of two variables? And so the result is that the expectation of the product, E of xy, is nothing more than taking the expectation of x, taking the expectation of y, and you multiply those two together. Seems fairly simple, but let's prove it to ourselves. And so let's make the assumption that x and y are independent from one another. And we have E of xy the product is equal to, there's our product between the two measurements, and then there's a joint distribution, P of x comma y, right? When I say x comma y, that's the same as saying x and y. They co-occur, or at least the measurements are co-occurring. And so let's make the assumption that x and y are independent, and let's go and prove this fact. Okay. So if we have e of xy, I make that substitution based on the definition of expectation. There's my xy random variable, so there's my xy values, and I'm going to compute the weighted sum, and so I'm going to multiply by p of xy. Now, of course, if x and y are independent, the probability of x and y is the same as the product of the marginals p of x times p of y. So I write out that expansion, and that expansion is exactly from the definition of what expectation is. So now I look at the indices on my summation symbols, and I look at my variables, and I'm going to factor out variables that are free variables under various indices for my summation. So I make the observation that in the inner summation, I have a y, and so everything that does not involve a y or a function of y is going to look like it's a scalar. So the x variable here looks like a scalar underneath this inner summation, the summation with respect to y, and likewise this probability of x is going to look like a scalar because it does not involve a y. So I'm going to factor out my x out of that summation. I'm going to factor out the p of x out of that outer summation. I'm going to put them right here between the summation with respect to x and summation with respect to y. And again, the reason why I can't factor them out from the other summation, the summation with respect to x, is because the expression x and p of x both involve x. They're not free variables under that summation with respect to x. So I'm left with the following expression for e of xy. I have my outer summation with respect to x, x times p of x, and then I have my inner summation, inner being to the right, with respect to y of y times p of y. Now if I look at this, I make the observation back up top for my definition of expectation. Well, this term is multiplied by this term, right? Because that's what factoring does. You have something multiplied by something else. And this looks a lot like e of x. Well, lo and behold, it is exactly expectation of x. And then this term looks like expectation with respect to y, right? And that's exactly what I get. And so I've proven the original statement. So that just says if you have two random variables, x and y, and if x and y are independent, if you want to compute the product of those two variables, the expectation of the product changes to be the product of the individual expectations. So you wouldn't have to go out and recompute the distribution. You just use this identity and just work forward with it. Okay. Any questions about this? Make sense? Okay. I broke my watch. I'm using my daughter, 7-year-old daughter's cat watch. So it's now, okay, we have some more time. All right, so let's move forward. Variance. Now, variance is a little bit more complicated, and we're going to make use of this FOIL rule that we talked about. The FOIL rule version where you have complex expressions. And so variance, the definition, Greek letter sigma squared, or Greek symbol sigma, but we square it. Sigma squared is the variance. And the variance, as we said before, is the expectation. So it's going to be a probabilistic, a weighted sum. And it's going to be that probabilistic weighted sum which measures the difference between the variable's value, x, and its expectation. So the spread between x and its center. And we care about the magnitude but not the direction, so we square it. Okay. And so if we were to write it with sigma notation, we're summing all values of x minus mu, so we take the difference between x and its mean, we square that, and we weight that by the probability of value x. Okay. And so what this result for the variance says, you might want to know, how does the variance change for a variable if I perform a transformation where I rescale it by multiplying by a scalar, and I shift it by adding a value? And it says how it changes is as follows. So if we have two random variables, x and y, and I multiply x by a scalar a, multiply y by a scalar b, and then shift it all by adding some value we're calling c, well, how that changes is I have a squared variance of x plus b squared the variance of y plus 2ab times the covariance of xy, right? So let's take a look at that identity. We're going to use all of the stuff that we've talked about, the associative rule, the distributive rule, and we're also going to use the FOIL rule, okay? All right, so let's start by just plugging in for what the variance means. Again, the variance is a weighted sum. We have the expression in the variance, and then we have a multiplication by the probability. If it involves two random variables, we're going to have a joint probability. So it's going to be probability over a random vector. So here we have two random variables. We have x and we have y. So the probability that we're going to use in the weighted sum for the variance is going to be a joint probability, p of xy. So that's why we have this p of xy. So now we have this expression minus its expectation, and we're going to square that. So here we have the same expression, ax plus by plus c, and we say minus the expectation of ax plus by plus c, and then we quantity square, right? That's just plugging in for what the variance means from up above, the definition of variance. Now, it just so happens that when we talked about expectation, that result we had called linearity of expectation, we're going to use that result here where we have this e of ax plus by plus c, right? We're going to use it directly. To jar your memory, let's go back a few slides. Linearity of expectation said that if I have expectation of ax plus by plus c, that's a times expectation of x plus b times expectation of y plus c. So I'm going to make use of that fact in the variance. Okay. So we have ax plus by plus c minus the expectation of ax plus by plus c quantity squared, right? So we're going to make use of linearity of expectation. We're going to replace that e of ax plus by plus c with the result we had from before. Okay, so we do that, and this is just a straight replacement. We say this expectation of ax plus by plus c, well, we have minus a times e of x minus b times e of y minus c, right? So we're just literally doing a replacement from what we had before for expectation result. So now we're going to group together some terms to make our life a little bit easier. Now, another way of talking or describing e of x, we said expectation, the Greek letter mu, is how you summarize expectation. And if we have more than one variable, we can write that variable as a subscript to tell us which expectation it is. So that would be expectation of x, and mu sub y would be the expectation of y. And again, the reason why you write mu sub x, mu sub y is so that you can distinguish one expectation from the other. Okay, so we're going to do that, and moreover, we're going to group together the a term with the b term, the x terms with the y terms. So we can write a x minus a e of x. Likewise, we can write by minus be of y, and then we can summarize this e of x so that we write ax minus a times mu sub x, where that mu sub x is just another name for the expectation with respect to x. So we do that both for the ax paired with the ae of x, as well as the by paired with the be of y, and then we also pair the c here with the other c. So let's see what we get. So if we do that, we have ax minus our a mu sub x. That's pairing the ax with the ae of x, and the ae of x has a leading negative sign, so we have ax minus a mu sub x. We have by is the second term minus b mu sub y, right? That's our second term, and then we have c minus c, which is our third term. So of course, anything minus itself is going to go to 0, so that term's going to go away. All right. So let's take a look at that. Any questions? All right. So the c term is going to go away. It's going to go to 0. And you notice here, for the first two terms, we have ax minus a mu sub x. We can factor out that common a, taking advantage of the law of distribution, distribution of multiplication over addition. So we factor out that a, we're left with a times x minus mu sub x. We do the same thing with these second two terms, by minus b times mu sub y. So we get b times y minus mu sub y. And all of this is quantity squared. Okay, and we haven't gotten rid of this p of xy. That hasn't gone anywhere. Okay, so now given this, we're going to apply the FOIL rule, and we're going to multiply out everything in this expression. And again, with the FOIL rule, we have this times itself, and we're going to treat a times x minus mu of x as our first term, and we're going to treat b times y minus mu of y as our second term. So the FOIL rule says we square the first term, we add it to the square of the second term, and then we add to that 2 times the first term times the second term, so-called cross terms, right? You can actually do first, outside, inside, last, but that's not incorrect. Talking about as cross terms is a more compact way of doing the FOIL rule. So let's do that. So if we have the first term squared, we're going to multiply this first term with itself. So it's going to be a squared times x minus mu sub x quantity squared, right? That's it times itself. The second term is going to be b squared times y minus mu sub y squared, right? Because a scalar squares if you multiply it by itself. And then the third term is going to be the cross term, right? So 2 times the first term times the second term. So if I multiply the first term times the second term, what happens? Well, I have the a and the b, so I get the a times the b, and then I have the x minus x mu, mu sub x, and then I have the y minus mu sub y minus mu sub y. Okay, and that's my result of squaring. Okay, any questions about this? And so literally, for this application of FOIL rule, you're treating this first term as a complex expression, the second term as a complex expression, and you're literally applying the FOIL rule to compute the square. And then of course, the p of x, y hasn't gone anywhere. Okay? Any questions? So if we do that, let's just writing it out in font, looks nicer, my penmanship isn't always that good. We get that expression, and it's literally just the application of the FOIL rule. We still have the double summation out front, and we have our p of x, y, our weighted sum on the back, and now we've applied the FOIL rule. All right, so now let's make another observation. Well, our observations are as follows. So we have a term here involving x's, but we have a summation here which is captured under the y. We have another term here involving y's, right? Here we have a summation with respect to x, and here we have an x and a y. The other observation that we make is we have 3 terms. Here's the first term, here's the second term, here's the third term. Now each of these terms, they're summed together, and we have a leading multiplication here times p of xy. So we could distribute this multiply by p of xy, it's just a function, for each term in this sum, and we can literally multiply this times the first term, multiply it by the second term, multiply it by the third term, and we're just literally applying distribution of multiplication over this addition. Okay, make sense? So you'll notice here, it's just making observations about patterns for what we see and application of these rules from algebra, okay? And a little bit of probability thrown in. All right, so let's do that distribution. So if I do that distribution, I'm multiplying this by p of xy. First I multiply it by the first term, multiply it by the second term, multiply it by the third term. So let's do that. So what we get, and you see this, you might be like, oh my gosh, that's really complex. But if you look for the pattern and remember the rules here, so here we have our first term, a squared x minus mu sub x quantity squared. There's my first term. I'm multiplying by p of xy. There's my multiply by p of xy. The second term, we had b squared y minus mu y quantity squared, right? We multiplied by that pxy. So there's my b squared y minus mu xy quantity squared, multiplied by pxy. This last term, 2ab, x minus mu x, y minus mu y, both quantities. Here's my 2ab, x minus mu x, y minus mu y, and multiply by pxy, right? So literally it's just an application of distributive rule where I distribute this multiply by pxy to each of these terms, the first, second, and third term, okay? Any questions about this? Make sense? Okay, so I have that big long expression. Now with this big long expression, I have 3 terms. These are pretty big terms, I agree. There's my first term, a bunch of stuff multiplied together. There's my second term, I have a lot of stuff multiplied together, second. And here's my third term. It's a pretty big third term. It's even more stuff multiplied together. So I have the first term plus the second term plus the third term. Okay, I would agree, you'd agree. So I take these three terms I'm adding together, and I have this summation here out front. That's the same as that simple example for which we used the associative rule. And remember, I had this thing where I had I goes from 1 to 3, and I said, here's my xi plus yi, right? And I said I could reassociate them with one another. Instead of summing the x to the y first, I sum the x with the x with the x and the y with the y with the y. And I can rewrite this. I goes from 1 to 3, sum the xi's together, and then sum the y's together. I goes from 1 to 3, sum the y terms, right? So that would be the same as if I just said, here's my x1, x2, x3, y1, y2, y3, plus, and instead of summing x1 with y1, x2 with y2, I'm summing all the x's first and summing all the y's first. So in this particular case, yes, it's a more complex expression, but it has the same exact structure as that simple example that we did before. So here, I have this parenthesized expression, and this parenthesized expression says, first, sum the first term with the second term with the third term, and then I vary my x and y, and then sum the first term, second term, third term. But I can associate together all the first terms and sum them together by themselves, the same way I sum together all the x's by themselves up here, right? So let's do that, and if we do that, we'll have a leading summation with respect to x and y for the first term, plus a leading summation with respect to xy for the second term, plus a leading summation with respect to xy for the third term. So let's go ahead and do that. All right, so I rewrote that expression just to have a clean slate here, and I will do that. So here we see the first term, and here's my leading summation. So I'm summing together all the first terms together first. It's just an application of associative rule. I do the same thing similarly with the second term. Well, there's my second term, right? It's the same as that second term, but instead of summing the first term with the second term with the third term, I'm summing together all the second terms under the summation separately, right? So there's that summation, and I do the same thing with the third term. There's my third term. Instead of summing my third term with the first term and the second term, I'm going to sum together all my third terms together under a summation, okay? And so that's just an application of associative rule for addition, and I'm just compactly summarizing them using my double summation. Any questions about this? Does that make sense? Okay. So now I make another observation. I look for a pattern, and I have my summation here in this first term. I have three terms. The first term is summing together, the second term sums, third term sums, okay. And I notice here I have that leading coefficient a squared. Now a squared does not involve x, it does not involve y. And so that looks like the result of distributive rules, so I'm going to factor that out, and in fact I can do that. So I factor out this common term a squared from each of these terms that are summed together with my summation. So I can write an a squared out front, and then I have my double summation, and then I have my x minus mu sub x quantity squared p of x, y. Okay, make sense? And I know my penmanship is pretty bad. So I do that factoring with the first term, and likewise the same observation with the second term. I have this b squared that does not depend on x or y, right? So I can factor that out as a result of the distributive law. So I do that there, and then likewise this 2ab, I can also factor that out. Okay, so I do that, and I have my leading a squared, my summation, the rest of the first term, x minus x mu quantities, x minus mu sub x quantity squared times p of xy. That's what I have here. I factored out my a squared. I factored out my b squared here, so I have the rest of the second term, y minus mu sub y quantity squared, p of xy. And then I factored out the 2ab up here, so I have 2ab, my summation, x minus mu sub x, y minus mu sub y, p of xy. Okay? Any questions about this? Make sense? So again, it's just an application of these two basic rules, distributive rule and the associative rule, and we also made use of the FOIL rule earlier on. Okay, so now that I have that, I make another observation, right? Well, when I have the definition of variance, remember we said sigma squared, our variance, is equal to E of x minus e of x. It was the difference, quantity squared. It was the difference between variable x and its mean. Its mean you can also write as mu sub x, right? So that's, notice here, well, let's look at this. We have x minus mu sub x, p of x, y. Okay, we can take care of that. We have y minus mu sub y, quantity squared, p of x, y. And then we have 2ab, we have our sums, x minus mu sub x, y minus mu sub y. Well, that third term, that looks a lot like covariance. It is covariance. But before we step through that, we can clean up the first two terms a little bit. You'll notice here, x minus mu sub x, that does not involve a y. And because it does not involve a y, it's a free variable underneath the summation, the inner summation with respect to y. So for all intents and purposes, that looks like a scalar under that summation. So we can actually factor out this x minus mu sub x quantity squared out of that first summation. And if we do that, we get an a squared, a summation with respect to x, and then we have our x minus mu sub x quantity squared, summation with respect to y, p of x, y, right? And the reason why we can't do it, factor it out of the left-hand summation with respect to x, is because this involves x's, right? You can't do that. So one of the things we'll observe here is that if we do that, let me see what my next step is. If we do that, we'll notice that we have a summation with respect to y and we have a joint distribution there, right? That's marginalization that we talked about. That's the same as saying p of x, right? And it's exactly like that problem with marginalization we talked about before, where we had the coin flip and the die roll. So we can take this whole expression and we take advantage of the factoring, right? And we take advantage of marginalization, and our result for that term is a squared summation with respect to x, x minus mu sub x quantity squared times probability of x. And that's exactly what the variance is. So that result is just a squared times the variance of variable x. Likewise, for the second term, we do the same thing, right? We can switch these summations so that it's b squared, summation with respect to y, summation with respect to x, y minus mu sub y squared, p of x, y, right? And so we can switch the summations because of associative rule. We can sum in any order we want, it's the same result. So if we do that, this looks like a constant underneath that inner summation, the new inner summation. So that becomes b squared, summation with respect to y, y minus mu sub y, quantity squared, summation with respect to x, p of x, y. Well, this is a marginalization. That's the same as p of y. So now we're left with b squared, summation with respect to y, y minus mu sub y, quantity squared, p of y. That's just the same as b squared times the variance of y, right? So it's the same procedure, just the variables are different. Now this third term, that's just the covariance. So that third term, and I was drawing an arrow down here, is 2ab covariance between x and y. Right? And I'll point you back to the definition of covariance a few slides earlier. So we have a squared times variance of x plus b squared times variance of y plus 2ab covariance of x and y. And that's exactly our original result we were looking for. Okay, so we've proven it. So again, it's just recognizing the pattern and an application of three simple rules: the FOIL rule, right, from algebra, associative rule, and the distributive rule. And summation is nothing more than just a nice compact way of summarizing what could ultimately be a very long expression. Okay? Any questions about this? Okay, so in machine learning and applied probability and theoretical probability, we use algebra all the time. We use some calculus too. We'll get to that later point in the semester. But what I really would hope you would do is not take my word for it. Actually get a pencil and paper and try it yourself, because it's really important to recognize when you apply these rules, and when you actually look at the structure of the formula and see the substitutions, it becomes a lot more comfortable to manage. Okay. Any questions? No questions? That makes sense? I'll try to post this. So if there are no other questions, we'll end here. It is almost 1:15, and we will pick back up with the balance of this on Thursday. I'll see you on Thursday.